Hey everybody, this is lesson 5.3, the conservation of mechanical energy. You've probably heard a variation of this law before. They say that energy is neither created nor destroyed. We're going to have a more mathy definition of it, and we'll dive straight into it. So this is the law of conservation of mechanical energy. Here's the way we'll phrase it. If friction and air resistance are absent, the mechanical energy of an object or system will remain constant. If friction and air resistance are absent, the mechanical energy of an object or system will remain constant. Here's that concept of never created nor destroyed, which means that the total energy will always be the same number. This concept here of friction and air resistance, these produce heat. So the energy is not being created, but it is lost in the form of heat. We won't go into that. We'll talk more about that in the next lesson. So here's the equation for the conservation of mechanical energy. It is EF equals EO. It's just that simple. For some change that occurs in a system or for an object, the final mechanical energy will be equal to the initial mechanical energy. It'll stay constant. By itself, that's not too profound, but it will be used when we expand it out to solve some pretty complicated problems with ease. If you recall from the last lesson, E stands for mechanical energy, and mechanical energy is made up of potential energy and kinetic energy. So we'll expand this equation out to include those things. Writing it like this, E sub Kf plus E sub Gf equals E sub Ko plus E sub Go. In words, this means the final kinetic energy of an object plus the final gravitational potential energy equals the initial kinetic energy plus the initial gravitational potential energy. We'll expand it out once more with the concepts of kinetic and potential energy. If you recall, kinetic energy is calculated by taking 1/2 mv squared. So let's substitute that equation in here. The final kinetic energy of some object that undergoes change is calculated with 1/2 times the mass of that object times the final velocity of that object squared. You could put mf for final mass, but the mass is probably not going to change, so why waste the ink? Plus mghf, that's the potential, that's the final potential energy of the object. EKO, it's going to look just like this one, but instead of final velocity, it's initial velocity. And there it is. This is the most general form of the conservation of mechanical energy. We'll very frequently use this because these m's can cancel out, as we'll see later. But I recommend starting here because sometimes you don't go all the way to this point. Maybe you'll plug in 1/2 mvf squared, but you'll leave this as EGF. Maybe you'll leave this as EKO and keep this as MGHO. So there's many ways to write this last form. That's why I think this is the best place to start. Start here. Best place to start. Now, that's it. That's the conservation of energy. We're going to use it to solve some problems. It makes a lot of crazy kinematic problems super easy. Like many problems where you'd have to calculate multiple velocities, use a bunch of angles, we'll be able to avoid a lot of that nonsense, a lot of that difficult math. So let's do it. 2 examples here. All right. Here's the first. All right, first one. Calculate the kinetic energy of a 1,200 kilogram roller coaster located 5 meters above the ground if it begins with a velocity of 8 meters per second and a height of 87 meters. Calculate the kinetic energy of a 1,200 kilogram roller coaster located 5 meters above the ground if it begins with a velocity of 8 meters per second and a height of 87 meters. You could draw this if you wish. I'm trying to save space. I want to solve the whole thing on this page. That'll be fine. Okay, so the roller coaster starts up here, goes down here. So we have 2. Try to visualize it. Maybe you can draw. I could do a quick drawing here. It doesn't have to be fancy. So here's the information that we have. The roller coaster starts up high, ends down low. The velocity at this location is 8 meters per second. Velocity at the bottom location, well, we don't know that. The height up top is 87. And the height down low is 5. I'm going to go ahead and add initials and finals. The roller coaster starts up here, so that's initial velocity and initial height. Roller coaster ends down here, so that's final height. The thing we're trying to calculate is not the final velocity. We want to calculate the kinetic energy. We're trying to calculate EK, EKF, or EKO. We want the kinetic energy while it's located 5 meters above the ground. when it happens later on. So that's EKF. All right. Let's go ahead and look at the equations. I recommend starting here. The reason being, this is the only one that includes EKF. Down here, EKF is hidden in this term. So it's best to start here and then plug in your three terms. So what we're going to do is take this equation. We're trying to calculate EKF, so we'll plug in these mini equations for each of these three. I think I'm just going to write that all in one step. So it'll be EKF plus MGHF equals 1/2 MVO squared plus MGHO. EKF plus MGHF equals 1/2 MVO squared plus MGHO. You might be tempted to cancel out these M's, but you can't actually do that here. In order to cancel out the M's, you need to have an M in all four of these terms, but we only have it in three. The fact that EKF is here rather than 1/2 MVF squared means that we can't cancel out the M's in the others. What we can do is solve for EKF and plug in everything else. So I'm going to subtract MGHF on both sides. And here's what I get. 1/2 MVO squared plus MGHO minus MGHF. And that's all she wrote. It's all math from here. The physics is done. So here we go. 1200 is our mass. VO is 8. I'll read this once after I plug everything in. Now make sure you know where each of these variables comes from. Make sure you know what each of these letters means. Here's what we have all together. EKF equals 1/2 times 1200 times 8 squared plus 1200 times 9.8 times 87 minus 1200 times 9.8 times 5. The cool thing about this is there's no, we could drop all these parentheses as long as we do our multiplication signs. You could type that in your calculator all at once and you should get a very large number, about 1 million joules. So 1,002,720 joules. There's our answer. So in order to calculate this problem without the conservation of energy, we would need a ton of information. We would need to know the angle that this track is sloped at. We would need to know the coefficient of friction. Remember that thing? Mu K. We would need to know that. Actually, the track probably curves a little bit. Probably curves this way, so it would actually be a problem that's impossible to solve for us without the use of calculus. So conservation of energy makes things a little simpler. We'll do one more example here. I'll leave it here. Okay, another use of the conservation of mechanical energy. In this problem, we are going to calculate the final velocity of the motorcyclist, and we'll draw the information. Calculate the final velocity of this motorcyclist. What this cyclist is going to do is rather unsafe. From the top of a 70-meter cliff, they're going to go flying off horizontally at a speed of 38 meters per second. You know, drawing is not my strong suit. That looks like a bike, kinda. Gonna leave the top of the cliff at 38 meters per second. It doesn't matter what angle they're going at, because the equation has nothing to do with the angle. It's gonna go flying off, and will land safely on a downward sloping ramp. Which is located 35 meters above the ground. We are to calculate the final velocity, the ending velocity that they hit this ramp with. For what it's worth, this must be the final height because it's located with the final velocity. The final height and final velocity are always paired up. That means this is the initial height and this is the initial velocity. The problem when we go to the equation is that there is no mass. So I recommend starting with this. I kind of want to contradict myself, but you know what, let's just do what I said originally. Okay, it's good to start here to check to see like, oh, did they provide the kinetic energy for me? Can I plug in a number to any of these? Maybe some of you will just be skilled enough to just jump to the right equation. I can see that this is futile, it doesn't do anything for me. Let's see if the next one works. By plugging in the next pieces, 1/2 mvf squared plus mghf equals 1/2 mvo squared plus mgho. So let's check to see what we have here. We don't have the m's, so let's try canceling them out. Let's see if this will be solvable then. Let's see if we can just plug in the numbers. VF is what I'm looking for, so it's okay that I don't have a number for that. Do I have a number for G? Yes, it's 9.8. What's the number for HF? Well, it's right there, 35. We're all good so far. What's the number for VO? 38. All right, that's good. 9.8 again, and 70. That's good. So this is solvable. We just need to rearrange. We don't know this. If for example, we were missing, like, if we didn't know the initial velocity, this would be an unsolvable equation, but since we have all the numbers except for VF, it will be solvable. So let's solve. I'm going to rewrite it. You can kind of skip this first step if you wish. 1/2 VF squared plus GHF equals 1/2 VO squared plus GHO. What we'll need to do is three things. We'll need to subtract GHF on both sides. We'll need to multiply both sides by 2, and then we'll square root both sides. I'll do them one at a time. One half VF squared equals 1/2 VO squared plus GHO minus GHF. The reason technically we're dividing both sides by 1/2, These are being multiplied, so we would undo this multiplication by dividing both sides by 1/2. But dividing by 1/2 is the same thing as multiplying by 2. So we'll multiply both sides by 2, square root both sides. I'll just do that in one swoop. So it's 2 times the rest of it. If you see any simplifications, you can go ahead and do that. For example, we could factor out the g. I'm just going to go ahead and plug in the numbers. So this problem would be particularly challenging without the conservation of energy. We would need to know the angle that he left at. It doesn't matter here. We would need to know we would just have to do a lot of little calculations along the way. We actually do have enough information to find it if we get the angle. But look at that. One step, no trigonometry, no angles. I think it's all plugged in correctly. And we're good to go. I recommend you try this one in your calculator. The last one is pretty easy. I recommend you try this in your calculator because, well, I made a mistake twice on it. The way to do it is, obviously do your square root. 2 times, and then the only parentheses you really need is this. You got to make sure you do that parentheses. I think your calculator is also going to open up some parentheses, so it'll automatically open up one right here. I'll make that purple to show it. So this will open up a parentheses automatically on your calculator. You don't really need to close it off, but you could do one there. Most important though, it's 2, and then you put all this. I would cut out every single parentheses here except for the red ones. Another thing, 1/2, it's better to do 0.5 in your calculator. 0.5 is much easier to do than 1/2. Once you throw in a division sign in your calculator, it can mess some things up. So give that a couple of tries. If you still can't get this answer, let me know. Either you're doing something wrong or I did something wrong. So our answer is 46.2. And that's our second example. So that's the conservation of energy. Yes, energy is neither created nor destroyed, but the important thing for us is that mechanical energy remains constant so long as there's no friction or air resistance. Our potential energy plus our kinetic energy is the same before and after. So that's about it. Go ahead, take a picture of these notes that you've done, post them on Google Classroom, and let me know about any questions you have. Have a great day, and I'll see you soon.